safe and sustainable. Yeah, I will talk about safe and sustainable by design and why it's needed for a circular economy, of course, as you said, Patty, in the context of the chemical strategy for sustainability. And now, does it move? Yes, it does. So this is just an overview slide that shows some of the elements in the chemical strategy for sustainability. And really the main focus here is to have a more preventive approach, that if we want to achieve multiple objectives to protect the environment and our existence, we need to consider not just one issue at a time, like zero pollution or climate change or circular economy or biodiversity. We have to think of it together. And the most effective way to do this is, rather than trying to minimize and control, which is very much how our system is today in legislations, there's an emphasis to say, well, let's go up and prevent the problems rather than trying and fix them once they have occurred. And really the focus is also that we shouldn't just solve one problem and create other problems. So as you see, there are many different elements in the chemical strategy for sustainability, all centered around avoiding harm to planet and the people, and a transition to safe and sustainable by design. And this little figure here is something that we have made at EEA to show as a kind of an icon for safe and sustainable by design. But a lot of it is really on the upstream prevention of risk, the non-toxic material cycles, safe and sustainable by design, and strengthen regulations. So just going back to like what is the issue? Well, exposure to the environment and people really happens along the life cycles. There's chemical input along the life cycles from the polymer production or like chemical production in general. In the product manufacturing, you might use some chemicals in the maintenance, and also in the waste management. If you do recycling and you clean your materials, you will end up using chemicals. And along these life cycles, you may have emissions to the environment and to people. And this little figure here shows that it's not just the environment, it's really also all the workers involved along the life cycles, from the production, manufacturing, and the end of life, as well as the workers applying it during the use of the products. Often we tend to only talk about the consumers, but really the chemicals are used especially by these people and in high amounts. And that raises the question, if we really are able to control the exposures, both if it's inside but also outside of Europe. If we make a product in Europe, let's say, but it's recycled elsewhere, are we sure that these workers are not exposed to that? And what about the vulnerability of these people and the communities around it? There's also an issue of cheaper products of recycled materials, for instance. In some places like China, they make specific materials for the Chinese market, the Vietnamese market, and Europe and outside, depending on the level of contamination in a product. And that raises this question about the equitable exposure and risk. So there's also that element of it. And we also know that the prediction of exposures is really difficult along multiple life cycles. In some cases, they're really impossible to foresee, and they're typically not included in the risk assessments. So just an example, which I should say, I'm thankful to Stefan van Leuven, who has provided this slide. It's an example of how building products was made into gravel, which was made in a hen farm, used in a hen farm, and where you had PCBs ending up in the eggs. During the risk assessment, nobody had thought about the building products to do a risk assessment for exposure to hens and going into eggs. Because at the time in the 1960s, 70s, etc., when it was applied, this was not part of the thinking. So it went from a foreseen use to an unforeseen use. Another example are plastics, not specifically plastic bottles, but just in general plastics, where you have one type of exposure, but then you end up using it, for instance, in toys, like nylon kitchen utensils, by the way, as well. And also there you can have unforeseen uses, and you can find high levels of brominated flame retardants and dioxins. So this is showing a little bit of the challenge we have with going from a linear economy with foreseen uses to a circular economy where we have multiple uses where it's difficult to foresee. But on the other hand, we know that chemicals really play a key role in either enabling or disabling a circular economy. Certain types of chemicals may increase the product longevity, also certain designs. We have this question of like how many cycles, so how many times is it going around in a cycle here? That's so going around once, it's one cycle, but then it's if it's recycled several times, we have multiple cycles. And how strong is the material or the chemical, and can it actually last through these many cycles and the different processing temperatures, etc., and stresses? It also raises the question of like how to do the metrics. Should we assess circularity in just in one cycle, or should we assess it along several years? If you take plastics, for instance, versus glass, you get a very different scoring if you just say during one cycle, then you have a lot of input of energy into glass and transport, etc., compared to plastics. But if you take multiple cycles, you may end up with a very different accounting there, because the glass can last for a lot more time and you don't have to re-extract resources. And along the ways as the materials degrade, you will have losses, but also so kind of intentional losses, you can say even energy to waste, but also like unintentional losses where you have leakages from the system. And in general, you can say that the complexity of the materials, the more complex it is, the more glued together it is as a multi-material, the more chemicals there are in it, the harder it is to keep the material cycles clean and maintain the quality of the product. So this is an example here showing that if you have plastics, again, I mean, ideally you want to end up with something that is recycled, which is very clean, but often you end up with something which is very mixed, and that puts a limitation on how you can reuse this later on. In the simple case where you want it to have a white product, it's very hard to get a white product. If you have something which is a lot of colors, you will get a brown or black product. But also when it comes to the strength of the material, it affects its performances there. Another thing is that if you then start to recycle it by cleaning it, you will use chemicals and energy, which is another type of input into the system. And really having clean materials is critical for obtaining consumers' trust and thereby expanding the circular economy. So this brings us to this other issue about tracking materials and chemicals in the circular economy. Here, the question is, do we have the available information along the supply chain, not just in Europe or inside the facility, but globally if we trade something on the market? What type of information is needed? Do you need information only about the current chemicals or also the legacy chemicals? Is that information available? Because maybe at the time it was produced, it was not considered a substance of concern, and therefore the information was not put in all the documentation of compliance. And also, what about the transformation products of the chemicals that are formed along the life cycles with heat or being used for containers for detergents or whatever? And that is then raising this question about like, okay, how much can you rely on documentation of compliance and passports, etc., versus what do you need to do in terms of backing this up with controls and testing? And this is just, again, thanks to Stefan Verleuven again for this slide, how it's normally done. You have and this is also, I mean, based on, I used to work as an analytical chemist for 15 years in research in the National Food Institute in Denmark, where I work with enforcement. And typically, of food contact materials, typically we would start out by saying, okay, we have some limits on some regulated substances, let's test them. So already there you have a tiered approach because you have chosen some chemicals to test and not others. And then you would set up methods for, depending on the type of limits, is it maximum limits or residue limits, or do you have specific migration tests limits? And then you would set up targeted methods if you could get the standards for them. Or you might set up group methods if the limit was associated with that. And you have that in food contact materials, but also in a lot of industrial testing where you have group of substances. But on the other hand side, we know that there's a lot more. So you might go into some identification of unknowns. And again, here you would then start by maybe a suspect streaming with a high resolution mass spectrometry or something like that. Or you might use some effect-based methods, in vitro methods, etc., effect-directed methods where you first test the toxicity and then you test the chemicals. Or you might go into some modeling. But the trouble is that while these are very powerful tools, it takes a long time. It can take literally half to whole years to identify just one sample for all the chemicals in there. And in the end, you have annotated a peak, and then you cannot get a standard, and you cannot prove its identity, and then you're back to zero. So in risk assessment right now, it means that you cannot use the data. So these tools are really very, very time consuming and also costly, and not very fit. They might be fit for a research project, perhaps in enforcement, but in the compliance testing along the supply chain, you need fast methods, cheap methods, and reliable methods. So that's a place where you have an issue. So coming back to like, what do we need? Well, we need products that are designed for a circular economy. And we need to consider whether fit for purpose is long-term use versus short-term use. So for instance, making coffee cups, styrene cups that last forever, like hundreds of years, when they're used for maybe at best 5 minutes, 10 minutes before your coffee gets cold, that's perhaps not fit for purpose. We need to think about products that can be repaired and can be separated so we can get clean material cycles. And also if we can reduce the complexity of the materials exactly to get the clean materials. We need to think about also the interdisciplinarity of the design process. So it's not just what I mentioned before about the study designs for the, let's say, to study the toxicity, etc., but also in the design of the materials to bring together different types of people, industrial designers, material chemists, toxicologists, the supply chain, and the CEOs, I guess. And for that, you also need some education so people can talk together and understand what is it, the purposes, what are we here for, and understanding each other's language. We also talk about that you need business models that has a focus on the service, which allows you to have a greater innovation space so you can deliver a service by many different means and designs. Think about leasing, extended producer responsibility to get information from so the producer gets the information from their suppliers, but also make sure that it works in the circular system, and etc. And then also thinking about the infrastructure and the investments into that infrastructure is really key. So this was like how we can design for products in the circular economy. But I think a key thing here is also to design it for the safety part. And here, the issue is that we see that exposures and the risk for substances of concern are foreseen to increase, both from the recycle of contaminated materials, climate change, where we have increased risk of accidents and remobilization of pollution. We see a global increase in production and consumption of chemicals, while we do not have a lot of data. And no data is not the same as no harm. So basically, because the exposure is foreseen to go up, the risk is foreseen to go up if we do nothing about it. Therefore, what we could do is we can try and bring the hazard down, and thereby we will have a decrease of the risk. And one of the ways to bring down the hazards would be to avoid using substances of concern. And there's been many people talking about this, not just us, but substances of concern are typically chemicals that lead to chronic pollution or chronic effects. So toxic chemicals, very toxic chemicals, and persistent and bioaccumulative and mobile chemicals. It could also be that we should go back to considering which elements we bring into our products, because we know that looking at, for instance, substances of concern, it's typically the elements like the halogens that create a lot of trouble, and a lot of the metals of different kind that also give trouble or that are very scarce. Whereas some other elements here, which are in nature, they typically are compatible with circularity. And this issue about reducing complexity is more of from a practical perspective, that it's much easier to overview life cycles and risks if you have a limited number of elements you have to deal with. So this brings us to the Safe and Sustainable by Design, and we produced a web briefing this year describing how this could be done, where we talk about the multidisciplinary design of a product, where you bring together people of different backgrounds to talk about what is the service you need, what should be the technical performance, consider how to make it circular by design so you can separate it, repair it, etc., and think about the chemical function there. It's really key that you avoid chemicals of concern, unless it's essential. And by essential, it means that, you know, it's not that it's essential for the company to survive, it's essential for a societal perspective, that it's really used for something that is very important to society and that it cannot be replaced. There are no services that can replace that service which uses the chemicals of concern. So in the next step here, we come into the describing the life cycles, which we need to do so we can do an assessment by some of the tools that were mentioned before. Modeling is a key element here. And in this first step, I forgot to mention that you select some candidates and then you start describing the life cycles of those, describe which impacts they are, and then you go ahead and assess the impacts. And this is where we still need a lot of research to understand how you can score these different impacts and what should be the criteria you compare against. And this is also where the Commission right now, DGRTD together with the GRC are working on developing the criteria. And finally, then you end up in a situation where you can go ahead and design the candidate products to produce. I just wanted to mention here that substances of concern are not the same as substances of very high concern, because already now you're not supposed to use SVHCs. And this is a little bit of an issue with the OECD definition, at least the guidance for alternative assessments right now. It is based on the minimum criteria is only based on avoiding use of SVHC. So you actually have to go to the extended criteria to have a safe and sustainable by design approach. Just a little bit about how this scoring could be done. Well, first of all, as I said, the ambition of the chemical strategy for sustainability is to meet not just one, but multiple goals at the same time and without compromising safety. So you need to bring in these different aspects. You need to have methods to score them into some kind of unit that can be brought together. And we also think that you need to set minimum criteria so you avoid greenwashing. So you don't say, this is very green because it has a really good scoring for climate, but if it really degrades the ecosystem or human health, it shouldn't be called safe and sustainable by design, because that would undermine the whole approach, including for all the other companies. We also think that if you want to get up with a final scoring of some kind that the consumer can read and understand, or the investors, we need to think about how you bring this scoring together. Maybe you weigh it, but we think also that there should be a maximum score. So within each category, you can only get a maximum set of points that allows you to calculate a total score. And these criteria for the minimum and total scores should really be informed by the protection goals of society. How much do we want to protect biodiversity? How much do we want to protect human health, etc.? That is not a scientific decision only. This is also a societal decision. Okay, so, and then to achieve this, we think that we need an enabling environment where we need to go focus not just on one thing, but we need to have the policies in place, the education in place, and also some technical support centers to support the industry. Here, the policies have already been mentioned, you know, the research policies such as the PARC and the public-private initiatives and the public-public initiatives like the PARC. chemicals policies, setting guidance for which substances to avoid. We need the products policies such as the Sustainable Products Initiative, and also investments such as sustainable finance criteria. And actually, safe and sustainable by design has made it into those EU environmental taxonomy for finance. I mentioned also education. I think really here we need to be able to understand each other, to sit together and design a product that delivers a service with the minimum impacts. And for the technical support centers, when we have the products out on the market, it's really important that you can compare between the different products, also if you need labeling. And to do that, you need to have some standardized documentation. Also, so the products that are made in Europe, for instance, can be compared with products that are imported into Europe, so we create a level playing field. And for that, you also need to consider really compliance methods that are fit for the supply chain. They shouldn't take a year to test, because then it just won't fly. So some of the tools that we could consider in applying here is, well, first of all, use the existing knowledge. There's already a lot of products out there that deliver service which is safe, so let's start simple and use those. Data mine for the families of safe chemicals. This is also where we could use many of the tools for hazard testing, etc. Modeling of the toxicity and life cycle exposures. But here we need really to think hard about how to do the gap filling when data lack. There should be some principles for it. And in the park, there will be some research to look into these principles for how to do the gap filling. We also need input on the data. Well, we need input data for the users, and this is a big gap we have for chemicals, because with REACH we have only ranges. We don't have the specific data on which chemicals are used for which purpose, and that really makes it difficult to do the modeling, but we still have to do something. And then there's the question about, like, do we model single substances or groups of substances? And this SSbD is really here up at the beginning, you know, before in the pre-market where the industry designs something, and you have
2 minutes left.
Sorry?
2 minutes left.
Thank you. Yes, I'm almost there. And then, so this is the type of data we need up here at the beginning. And then once it gets into the market, we need the information on the compliance testing, and including methods of in vitro, in vivo, and silico for hazard testing. And again, perhaps we should start simple and effective and use the substances of concern, and then over the time, the models will probably be developed. So just 2 very quick examples where I think this could really be applied. We see a rapid upscaling of renewable energy technologies, but the question is, do we have the assurance that we actually have infrastructure that can treat these products at the end of their life? For instance, lithium batteries have 1 to 2% of fluoropolymers in them, and the lithium is often recovered by heating it, and heating it at so low temperatures that these fluoropolymers do not fully degrade, but they form F gases that are greenhouse gases, and also ozone depleting substances, plus as well substances like trifluoroacetic acid, which are persistent mobile compounds that is a problem for the water. Another example of the lithium batteries is that you need ionic liquids to make them work. And I recently learned that one of the ionic liquids that are used is another PFAS, which is a persistent mobile compound. Very persistent chemical, and it's either mobile or very mobile and potentially toxic. How will these liquids be collected at the end of the life, especially if you scatter them around desert? And who is going to pick them up there and make sure that we don't pollute something? So these are just some examples of where I think we really need safe and sustainable by design right now to think about it, and also think about how we can separate the materials. So with that, in conclusion, we need safe and sustainable by design to unlock the circular economy, because these the future exposure pathways and uses are really difficult to foresee. testing has to be fit for purpose, and it's simply very, very costly and time consuming to test for all harmful substances. And we need to think about how we can solve multiple challenges. And when we are rethinking of the environmental challenges, so that we don't solve one problem and create other problems. And in doing that, we have to think about how products are made. We have to think about why are we creating products, focus on the service. How do we want to deliver the service? By which product? Which materials do we use? Which chemicals do we use? Can we start by avoiding substances of concern? And then we need to create an enabling environment that allows industry to really do the innovation they can. And they will really need a lot of innovation to deliver the same services, but perhaps with less harmful chemicals. And with that, I want to thank you for listening.
Thank you, Xenia. Really wonderful presentation. I think it wraps up everything nicely, and it shows us the difficulties of everything, of course. So